Hello friends, welcome to Mu Lessons. Previously we have given some videos on the basics of FETs and MOSFET. Now we'll see the internal structure and how actually what happens in case of FETs and MOSFET. So this is just a simple picture of physical structure of enhancement type NMOS transistor. These types of transistor consist of some parts like the source region, drain region, oxide region. It has terminals, 3 terminals, basically the source, gate and the drain. Now this part is called the channel region from which the electrons has to flow, and this whole gray part is the P substrate body or the body. This is the vertical overview, you can see. So we'll start with FETs, that is the field effect transistors. This FET basic operational theory, is the current control mechanism, that is the current drain current is based on the electrical field established by the voltage applied to the current control gate or the terminal. Now the current is only conducted by one of the type of carriers, that is electrons or holes. That is why sometimes FET is called the unipolar transistors, and another type of insulated gate FET is the IGBT or MOSFET. Now why MOSFET are used as transistors and why they are basically used? Because of some advantages. These are very smaller silicon area on the IC, and they can be used to make integrated circuits, simple to manufacture, no need for biasing resistors, the pull-up pull-down resistors. They are basically used in VLSI designs, and the enhancement type MOSFET is the most significant semiconductor device available today. So it is very much widely used in making the electronic systems and circuits. Now this metal oxide semiconductor MOSFET has been extremely popular since 1970s, and compared to BJTs, MOSFET transistors can be made very smaller or more smaller than the BJTs, easy to fabricate. They have simple circuitry for logical control or the digital logical memory, and inferior analog in circuit performance, that is a low gain. Now most digital ICs use MOS technology these days, so the trend is to use the implemented in MOS technology for the low cost integration and digital circuits in the same chip. Now we'll study about the device structure of FETs, that is the field effect transistor. It has 4 terminals, basically the gate, drain, source, body. And unlike the BJTs, MOSFET is normally constructed as a symmetrical device. The name MOSFET, metal oxide semiconductor, is apparent from the structure. Typically the length is from 0.15 to 10 micrometer. The width, you can see, follow this diagram. The width lies from 0.3 to 500 micrometer, and the thickness of the oxide layer is in the range of 0.02 to 0.1 micrometer. Now the minimum value of the L achievable in a particular MOS technology is often referred as the feature size of the technology. State of the art that some of using is Intel Pentium 4 uses this type of technology, and modern technology uses polysilicon, which are very high conductivity, instead of metal forged from the gate. This is a circuit diagram of E-type FET, JFET, means enhancement type. The enhancement type NMOSFET has a positive voltage applied to the gate. Now this positive bias voltage enhances this layer to be opened up for the drain current to flow. An N channel is induced at the top of the substrate beneath the gate, and this channel is very much helpful, or this channel is the main reason for the flow of electrons and current, and it is very helpful in case of construction of this circuit. Now an NMOS transistor with VGS which is greater than or equals to VT, let VT is the thermal or the threshold voltage. Now when VGS is greater than the threshold voltage and with a very small VDS applied, the device acts as a conductance whose value is to be determined by VGS. Specifically, this channel conductance is proportional to VGS minus VT, and this ID is proportional to VGS minus VT into VDS. So generally IG is to be made positive, and this positive, now just imagine what happens in this case. This is N channel means n-type material is doped on a p-type substrate. Okay, fine. Now this is an n-channel e-MOSFET. Now how can you make this n-channel? If you apply forward bias, if you apply positive voltage across this gate terminal, then these n channels electrons in this part will be attracted and this channel open up. So this is the basic reason why it is been giving forward bias through the gate potential, and this positive potential enhances the n channel and makes the path easier for the flow of current. The circuit symbol, the arrowhead on the source terminal points in the normal direction of the current flow. Therefore it shows three things, that is distinguishing the source from the drain, it indicates the polarity of the device, and designates the terminal also. So that is the basic use of this circuit symbol. It will distinguish the source from the drain. You can see how it is distinguishing the source from the drain. The upper part is kept the drain, the lower part is the source, indicates the polarity. It can be n-type or p-type, and it designing the terminals or designating the terminals. The names of the terminals has been mentioned in this circuit symbols. Now there are three regions: cutoff region, triad region, and the saturation region. So in case of cutoff region, the gate source voltage is less than the threshold voltage. So what happens in this case is the gate voltage is not able to reach the threshold voltage and it is still less. So this is the cutoff region. Now at the triad region, this VGS is greater than VT or the threshold voltage. So little bit it starts conducting. This is the locus. This is the triad region, or you can say the ohmic region, in which it behaves non-linearly, and as this VGS is very much higher than the thermal voltage or the VT, then a large amount of current flows, or this is the saturation region in which a constant current flows, and these things can be only controlled by this VGS or the gate potential. So this gate potential has a very important role in case of field effect transistors and MOSFETs. Now this little derivation of ID and VDS relationship. Now the electron charge is in an infinite small portion of this channel. dq is given as minus COX, that is the capacitance of the oxide layer, WDX into VGS minus VX minus VT. Now COX is the capacitance per unit area of the oxide layer, that is equals to permittivity of oxide E epsilon OX by TOX. TOX is the thickness. Now current is given as I dq by dt, so dx will be minus mu n En. You will see these things in physical in the study of PhD, physics of semiconductor devices, also in the 3rd semester, 4 semesters. So just for now you have to go through these derivations of the relationship between ID and VDS. Now this current I must be constant at all the points in the channel and be negative the drain current ID. So ID is given as mu n COX, or the capacitance of the oxide layer, into W into VGS minus VX minus VT into dVx by dx. So we obtain the ID/VS characteristics of the triad region as follows. ID is given as mu n C W by L VGS minus VT into VDS minus half VD square. So the expression for saturation region can also be obtained. So remember, in case of saturation region, I have told you VGS minus VT is equals to VDS. So we can replace this term by VDS and we get ID equals to half mu n C W by L VGS minus VT whole square. Now you might be wondering what this term means. This is the processing technology. It is a constant determined by the processing technology, and generally it is determined as K, denoted as K. Now this is the basic difference between the saturation region and the triad region. Whenever VGS minus VT is equals to VDS, it comes to the saturation region. Now for a triad region, the equation is given: ID equals to K, Kn is the processing is a constant, mu and C, Kn W by L, VGS minus VT, VDS minus half VDS square. So however for small VDS we can say that this half VDS square approaches 0, and this equation results into this following equation. Now from that we have to find the drain to source resistance. This RDS, drain to source resistance, is given as VDS by ID. Now we can replace VDS by ID as 1 by K and W by L, VGS by VT. As we have seen from the previous equations, ID by VDS can be replaced in this manner. Now if by knowing the values of Kn, VT, W and RDS, you can easily calculate the value of RDS. Just put the formula and get the answer type questions. Now this is another use of FETs as CMOS. This is a cross-sectional structure of circuit diagram or circuit. This is a cross-sectional structure of CMOS integrated circuit. It is a combination of PMOS transistor and NMOS transistor, so it is called a complementary MOS. Note in this case the PMOS transistor is formed in separate N-type region known as N-well, and another arrangement is also possible with N-type body is used and the N device is formed in a P-well. So any of these two methods can be used, but as it is a complementary MOS, these are made of two types, it is NMOS and PMOS, combination of NMOS and PMOS separated by a thick silicon dioxide isolation. N-channel FET, that is the N-channel enhancement type FET with VGS and VDS applied with the normal characteristics of the current as been shown in this diagram. So already we have seen how the relationship between VGS minus VT and VDS, the relationship between all these three depends or gives the region, either it is cutoff region, triad region or saturation region, and so on. So you can get many informations from these variables. So these are just the plots of enhancement type E-type FETs. Now this plot shows the effect of VDS and ID in the saturation region. The MOSFET parameter VA is typically in the range of 30 to 200 volts, and generally all these plots mainly depends upon the voltage VGS. As the voltage increases, then the saturation becomes more steeper. With low VGS there is less steep and we get the saturation current more easily. Now once the MOSFET enters into the saturation mode, increasing the VDS beyond VD saturation, it will move into the channel of pinch off voltage or the pinch off point slightly away from the D to S. The effect channel length is reduced in this part. Now since we know that ID or the drain current is directly proportional to W by I from the formulas, you can see this ID is directly proportional to W by I, so the drain current will decrease accordingly, and this phenomenon is known as the change length modulation effect. This channel length modulation can be analytically encountered by incorporating a factor of IV equations. By the study of these IV equations, you can easily find the phenomenon how this channel length modulation effect changes with respect to whenever there is a change in W by L ratio, there is a change in ID current. This is somewhat similar to what you have learned in BJT, that is the early voltage. Similar to that of early voltage in BJT, we will refer to as the early voltage. Typically in this case lambda is from 0.005 to 0.05 volts and corresponding VA is in the range of 200 to 20 volts. Now the best approach is by drawing the small signal analysis and finding the values. So this case shows the three regions: cutoff region, triad region, saturation region. In case of cutoff region, VGS is less than the threshold voltage. In case of triad region, VGS is greater than the threshold voltage, VGS is greater than VT, means just on the verge of conducting. Now in case of triad region, VGD is equals to VGS plus VSD. So we can easily say VGS minus VSD is greater than VT, so it comes under the triad region. Similarly, for VGS to be greater than VT and along with that VGS minus VDS should be less than VT, then it will be operating in the saturation region. So these are some variables which are very useful for deciding the regions in which this FET is operating at the particular instant of time. So these small signal analysis are very much useful for the calculation purpose. Now in this case, we need to consider some practical things like the breakdown and input protections. There is an avalanche breakdown of the PN junction between the drain and substrate at the voltages from 50 to 100 volt. Punch through about 20 volt, the depletion region surrounding the D extends to the channel to S when VDS increases to a certain point, and the gate oxide breakdown in this case when VGS exceeds about 50 volt, resulting in the permanent damage to the device. Protection devices are needed at inputs. Now what is the effect of temperature effects in this case? Both VT and K dash are temperature sensitive. The magnitude of VT decreases by about 2 millivolt for every 1 degree rise in temperature. So you need to remember this point, it is very important. The magnitude of this VT increases by about 2 millivolt for every degree rise in temperature. This decrease in VT gives rise to a corresponding increase in the drain current and the temperature is increased. But however, because K dash decreases with temperature and its effect is in dominant one, the overall observed effect of the temperature increases in the decrease in the drain current. Now the depletion type MOSFET has a similar structure to that of the enhancement type MOSFET, but with one more important difference. The depletion type MOSFET has a physical implanted channel. In case of depletion layer MOSFET, it has a physically implanted channel. Thus an N-channel depletion MOSFET has an N-type silicon region connecting to the source and the drain, both for the positive and at the top of the type of the substrate. Thus, if a voltage VDS is applied between the drain and the source, a current ID flows from VGS at VGS equals to 0. Whenever the gate current applied is 0, then if a voltage VDS is applied, then it is flowing. So there is no need to induce the channel in case of depletion MOSFET, it is already present. The channel depth and hence its conductivity is controlled by the gate voltage or the potential of the gate or the VGS. Applying a positive VGS enhances the channel by attracting more electrons. As I have said before, the positive voltage at the gate surfaces enhances the channel by attracting the more electrons and it makes the channel open for the flow of current. Similarly, these are some diagrams of FET in depletion type. These are the same applications, same formulas are used in this case also. Now VGS is positive for the transistor to be operated in the enhancement mode type, and VGS is negative for the transistor to be operated in the depletion mode type. So you need to remember these 2 points. For FET to be operating in the enhancement mode, we should apply positive VGS or the positive gate potential, but in order to operate the transistor in depletion mode, we need to apply negative VGS or the negative gate potential. For the transistor to operate in the saturation region, I have already told this VDS drain to source voltage should be greater than this threshold voltage. Now these are many practical applications. Normally on devices, a thin N channel layer is implanted for NMOS and VT is negative for these types of NMOS. Now in this case you can see for this depletion region, this graph is particularly very beautiful graph, giving you many ideas regarding how can you operate in both enhancement and depletion mode. So whenever VGS is 0, you can find the saturation current line this form. Whenever VGS gets positive, we get to operate the device in the enhancement mode, and whenever it is negative, we get to operate in the depletion mode. So there are many such applications of FET, and we will see about some of these applications and circuit diagrams in our next video about the MOSFETs. But I would request you to go through the book, because until you will read yourself, you will not get the actual idea, and if you have any doubts, you can ask us. Thank you.